Okay, so I promised you this time that I'm going to go through and collect information and try to put something more rigorous together. So I did talk to some experts in the field, and I went through literature, and it really is kind of sloppy put together so far. You can take a look yourself. It's very, well, you're going to have to for your project, so you'll come across this as well. So what I did is I ended up taking material from a variety of places. There's a set of books called Winning Ways for Your Mathematical Plays, and it's a 4-volume set of books, and they're like Led Zeppelin albums. People don't return them. They're actually, you can't buy them used without paying a lot of money for them for some reason. So I never got them, but I can access them through the Columbia website. So I used those 4 volumes. They're very weird. They're not like a textbook. They're not set up where everything's structured and they have something building on top of something else. They'll have something about domineering in volume 1 and it'll reappear in volume 3, and they'll say remember that in chapter blah 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 in volume 1. So it's scattered all over, and also there's no structure. It's kind of like what you see in your book where they're defining something like saying, oh well, it's this and not this. It's not a really structured definition. I also took some papers. There's a paper on games on triangulations, which is in Theoretical Computer Science, 2005 publication, really nicely written. So that's why I kind of felt that that was a very good article. And then we were getting deeper into graphs, games on graphs. All combinatorial games can be expressed as a graph. And when you recast these games into a graph theory notation, then you can make it more rigorous. So that's where I want to go, because that's where you're going to have to go. If you take a game, you're going to have to figure out how to formalize it and make it a mathematical object. And saying it's something like this and something like that, that's not mathematics. That's something else. It's the guy on the street talking to you about games. It's not the same thing. So I just took it out of these sources, and I wanted it recorded that they're coming out of these sources. It's some of it's coming, the seeds are coming from your book. So it's a little messy, so I want to give you the order of how I went about things. First, I went to the questions I have. What's the list? What is bothering me? So I wanted to go through that list with you. The second is I wanted to find rigorous definitions and descriptions to set the stage. I need to know where they're framing things from. For example, if they're talking about a loony move, I had to go back in time to figure out where they came up with the structure in the first place to define something called a loony move. And then I try to answer my questions as much as possible. I did end up buying the Dots and Games book that Berlekamp wrote, but I don't think that it's going to give me more insight, but let's see what happens. And then I took a related game on triangularizations, and it uses graphs, so I'm going to show you that. And then the very final thing is game graphs. How do you restructure everything and pose them as a graph? I also used Games of No Chance. It's not as structured either. It's a series of papers collected into a book. I think it's just a new area, and that's why you don't have much structure. And I'm used to working in old areas like real analysis, so I'm not used to seeing this. And in the past, I worked with a game theorist, so he was able to write things on the board, so I didn't really have to rely on anything else. Okay, so we can't avoid things any longer. We really need to formalize dots and boxes carefully, because the book keeps drawing on this and they're using terminology that's not well defined, so I feel like I have to go there. So that means we need rigorous definitions. We need clear examples. One of my sources of irritation is that there's no examples. And in anywhere I look, they talk about loony moves and this and that, and they show 1 or 2 pictures. I need to know exactly the definition, and I need to know what the example is of a loony move and an example of something that's not a loony move. And if you had a theoretical class for me, you know that that's how I structure my theoretical classes. So I'm very irritated not to see that. And I also need clearly stated theorems. I feel like the theorems we've had so far are just, they're not clearly stated, and it's annoying. So what do we know so far about dots and boxes? We know if a player gets the right number of long chains, they can win. Kind of. It's not really, I'm not comfortable with what they're saying. It's like, kind of, if you get some long chains, you might win. I need a very clear definition of long chain and can win. Those 2 things need to be clearly defined for me, otherwise I feel I can't move on. We also know from class play that winning on a large size board is easier. My mathematical mind says, ask the question, why? Why is it easier? When something's easier when the board gets larger, it means that you're heading towards some kind of asymptotics. So there's some kind of long-term behavior that's being exhibited that you see in the larger board. And then I have definitions I want to know. What's a loony move? What's a loony position? What's a loony endgame? What's a loony stage? These four terminology I've seen scattered around your book and in papers, but I haven't seen a formal definition of what this is. I have an idea, but that's not good enough. And they also talk about double dealing and double cross positions. I showed you some examples. I didn't feel so comfortable with those examples. They came from your book. They had, this is a double cross move. This is a double dealing move. And they don't really say, this is the definition of a double cross move. And this is the definition of a double dealing move. And here are the examples. So I wasn't satisfied, as I think you should not be satisfied and say, I know what that means 100%. So let's start from the beginning. What do they mean by a combinatorial game? There's a definition that's out there. There's two players. One is called left and one is called right. You can imagine two players sitting at a table. One is called left and one is called right. Or oftentimes you'll have player one and player two. There's usually several, finitely many positions, and often a particular starting point. You have to start somewhere. There are clearly defined rules that specify two sets of moves that left and right can make, like in dots and boxes. You can put horizontal or vertical lines from a given position to its options. Left and right take turns, move alternately in the game as a whole. In normal play convention, a player unable to move is the loser. The rules of play will always come to an end because some player will be unable to move. That's how we always end these games. Like somebody's unable to make another box, or somebody's unable to take another coin, so forth. And both players know what's going on. So there's no hidden information from the other player. And there's no chance moves. So you're not talking about dice or spinners. There's no probability involved. So what games fall and don't fall under these conditions? That's what we didn't do. And I want to do that now. Backgammon. How many of you played backgammon before? Like this boring game they take out on Thanksgiving. Right. So does that fall into that category of, why does that not fall into the category?
It has chance.
It has chance, has a dice. So these games use dice, so that's a no. Rock, paper, scissors. Is everyone familiar with this game?
Yes.
That's how you decided to take my class, right? So what do you think? Does that fall into the category of a combinatorial game? And if it doesn't, why not? That's exactly right. The other player doesn't have complete info about the opponent's move. That's what makes rock, paper, scissors work. And also, you don't take alternate turns, right? You're like at the same time. Except they, when they don't do it quite exactly at the same time, they start yelling at each other that they cheated. I have an 8- and 9-year-old. What about tic-tac-toe?
Yes.
Satisfied? Ever had a tie in tic-tac-toe? A draw? Yeah? Yes.
Yeah.
It can happen. No, because a player who's unable to move is not necessarily the loser, right? You can actually have a draw. So that's not a combinatorial game. What about chess? Can have a tie. That's a problem. No, there's ties. Stalemates are possible. So that's not a combinatorial game. NIM is very obviously a combinatorial game. But I was surprised. Does dots and boxes satisfy the combinatorial game definition? It actually doesn't. Because the way you win is by the winner collecting the most boxes, not because the winner is unable to move. Right? So it doesn't identify exactly with the definition, but it shares some of the categories, and that's why we talk about dots and boxes. Okay, so I went to Winning Ways, and I wanted to see if I could figure out from the really frightful definitions that they have in Winning Ways Volume 3, what they mean by some of the definitions they're talking about. So this is an empty set right here, and where some of it's been filled in for dots and boxes, 4x4. And if the next player that goes, let's say it's Alice, that goes, takes these two boxes because it's easy to do so here on top. You see that they've covered it up, they get those two boxes, and they put a box down here. what they've effectively done is they've left open a chain. And as we know, chains are not a good thing if it's your turn and you opened up a chain for the other person. What this person's going to do is they're going to box up and take this one. When they do so, they give up these 2 boxes to A. And we've seen that before, the giving up or the sacrificing of 2 boxes. What happens then is that player B can capitalize on the fact that there's a long chain and then start to fill in all of the pieces at once. And that's what you see when you play dots and boxes against the computer, isn't it? You're trying to play strategically, you're trying to map out what you're going to do, and all of a sudden you click one of these things through and you see it just filling up with the computer boxes. Isn't that what happens? So this is exactly why it's advantageous to have a long chain, because one by one you can siphon off all the boxes at once. So what's a double dealing move? It's a move where a player sets up a play to force their opponent to take 2 boxes in order for them to open up a chain. That's what a double dealing move is. So here, Bob left the board like this. It's Alice's turn. Alice closed up these things. So the chain is laying there. So because Bob left it so enticingly, and Alice just went and grabbed her 2 boxes. She played greedy and she took those 2 boxes. So Bob set up Alice to leave this long chain open for Bob. And why did Alice put this here? This is a move that I would have made. So that Alice can't close up more boxes, because if he puts it here, then she can start getting 2 boxes, right? So if he puts it here, it gets more difficult. So that's what a double dealing move is. It's the fact that it forced Alice to take those 2 boxes on top, or it enticed her. So it's not forced, it just enticed her. So what's a double cross move? It's a move where 2 boxes are completed with a single stroke. So here we have this thing right here. A double cross move is when this happens. That's the definition of a double cross move. So the strategy, question?
Are those names specific to dots and boxes, or can they?
Yes, they are.
Okay.
Yes. Yes. They have some more. They have a heart, something with a heart in it. So I didn't want to go there. I was already annoyed enough that things weren't rigorous. But I understand these 2 things. The double dealing move is to entice the person to grab 2 boxes so that it leaves a chain open that you can capitalize on the end. A double cross move is when you take 2 boxes at once.
Because they have they paralleled it in the book with the coins.
The coins, I'm getting to that. So when I saw the coins, I immediately thought vertices and edges. That's what that is. And so I started thinking about graphs, talked to Dr. Cutler, and opened up some new books. And I think that's where I want to go, because I don't think I can keep going this way too much longer. So the strategy to me is vague. Be the first one to force your opponent to open a long chain for you, and decline 2 boxes of every long chain except the last one. And you see that strategy being handled, and sometimes if you played the computer did that to you. Enticed you to grab 2 boxes, you got those 2 boxes, maybe you get a 3rd one, and then you're 3 against 6. Correct? I had a 3-6 quite a few times. So that's what it does. That's what the vague strategy. So what about this loony language? It apparently this language actually comes from a different game called Nim Strings, which is similar to these strings and coins, which I've used to decorate the PowerPoint. So it comes from the Nim Strings, but when I went to the Nim String literature, it's also badly defined. So I started looking around where I might find a good definition of what they mean by loony. So I want to show you a different game. This game is on a graph. So there's games on graphs, and this is one of them. It's very nice. It starts out with what we call a triangularization. There's a center vertex. So we have a center vertex right here, and we have vertices surrounding that center vertex, and they're all connected. So this is what we call a connected graph. I'm going to give you formal definitions of graphs and all that stuff coming up. The players take turns coloring. So for example, first player might color one of the edges on this piece. Second player might color that one. So the pink player might color that one. Green player might color that one. Pink player may color that one. Whenever they finish off a triangle, they get the triangle. So the green finished off 2 triangles now on their turn. So they grab those 2 triangles. Very similar to dots and boxes. So we go, continue on, and they have to go again. They get the box and they have to go again. So there they go again. They get that box. The pink gets that box and makes this line down here. And green's able to finish the whole thing. So green wins. So what I'd like you to do, because this will make it very clear. The game on the graph makes it clear, even though it seems like more notation won't make it more clear. So what I'd like you to do is to play triangle color games, just like I showed you, but make extend the vertices. So start out with 4 vertices. That's kind of as small as you can go, and play it with your partner. And then extend it to 5 vertices, 6 vertices, and 7 vertices. And then fill in a table. What'd you find? In 4 vertices, you should be able to figure out a winning strategy. Does the first player win? Do they not? Start and then next extend it to 5, extend it to 6, extend it to 7, and so forth. Just tell me what you found in each one of the games, if you're able to generalize in any way. Describe how things change when you add more vertices. So you can add more vertexes around. Does it get more complicated? Is it harder to play it? In dots and boxes, it isn't. A lot of you told me that the app is not a 4x4, that the app is actually a bigger one, and you found it easier to play when there's more. Is it easier to play here when there's more? Does it get easier or harder for the first player to win when you add more vertices? Does it matter whether n is even or odd? We've seen that parity is a huge deal. I mean, and it's because they're taking turns, right? So is it easier? Does it matter whether n is even or not? I would think it should.
The first one is it's like 4 on the outside. 4 and then 1 in the
Yeah. Right, because you have to be able to make triangles.
So 3 and 1.
Yeah, why? How is that 4?
You have a center vertex too.
Yeah, 4 vertices.